Welcome to another video from Roland Mösel, founder of planetary engineering group Earth. Now it's about the summer-winter balance of electricity. We make this not with a country or a whole continent because this is very complicated. We break down the problem to one single house, a GEMIN next generation house equipped with 30 kilowatt photovoltaics, 70 kilowatt lithium iron phosphate batteries, and 1000 kilowatt hours of low temperature heat storage. For this, the house is very well equipped for day-night balancing and different weather conditions over a week or so, but now it's about summer-winter balance of electricity. Let's look about it at 7 different locations. Let's start far in the north of Europe in Oslo. What you see, there is nearly no electricity production in winter, in December. Only 64 kilowatt hours produced by 30 kilowatt photovoltaics over 1 month, the whole December. A little bit south is Berlin. We have here about 5 times more in December. We go a little bit more south to Vienna, nearly double as in Berlin. We go down to Rome, more than double in Rome. And again a little bit south, no much difference to Athens, and again a little bit south, Tel Aviv. Here you have again a big jump. We have over 2000 kilowatt hours in December, and even a little bit more south to Cairo. Here we have a table about all the cities and all the months. In June, there's only 1 to 1.4 difference between Oslo and Cairo. Not so much, but in December the difference becomes dramatic. There's a 1 to 40 difference between Oslo and Cairo. Let's look the best against the worst months. There is a 62 to 1 difference between June and December in Oslo, but the difference here we have July because of weather conditions. July is a better month than June in Cairo. We have only 2.2 to 1 difference between July and December in Cairo. Now let's look on the electricity consumption. We assume for every month 600 kilowatt hours electric consumption for household, domestic hot water, and electric cars. This is 7,200 kilowatt hours a year. This is a big consumption, but it includes electric cars. And then we have a table for the additional demand for space heating and cooling. Here we have in also assumed in December and January 500 kilowatt hours, and more in the south this goes much down, and starting in Vienna we have in the summer a cooling demand, and more south this cooling demand goes over more and more months of the year that it's necessary to cool down the house. Summer and winter compensation is only required from Vienna to Oslo. All the other locations have enough solar electricity even in December. Now, what to do with this problem? Fortunately, most people live in latitudes where the difference between summer and winter is small. So this is mostly a North and Middle European problem, because nowhere else on the world are so many people living in such high latitudes. Proposal 1 for solving the problem. Let's take twice the photovoltaic. where to put it on a small building ground, it's a little bit difficult, but doubling the photovoltaic helps only in Vienna, and Berlin and Oslo still remains with not enough electric power for the winter. For Oslo is twice almost nothing is still almost nothing. We have twice of 64 kilowatt hour monthly yield for December, or it's still much, much too less. Proposal 2, much more batteries. Here I calculated all the electricity demand, what is not yield in the yellow months, and I put 25% additional because there is efficiency, there's self-discharge of batteries when over 6 months. So it's 25% more batteries than the calculation what is needed. And it's extremely expensive. Why? There's an old spell, money has to work. A battery has also to work because a battery costs much money. And if the battery works 300 times a year, then it's very economical. But when the battery works only 1 time a year, then it's very unaffordable. So let's look for a cheaper solution. Proposal 3, hydrogen. There are these 12 items with compressed hydrogen gas, and it's 1,616 euros without value-add tax. And in all this, you have a storage volume of 600 liters. And all this is 1,460 kilos. It's very heavy, it's very bulky. And now you think how to calculate what you can put in this. But it's wrong. Because sure, you think there is the ideal gas formula, and I have only to say 0.6 cubic meter times 300 bar times 0.09 kilo of hydrogen gas, and then I have the result. No, the ideal gas is not in all pressures. It's on the beginning of this curve. It's very close between the ideal gas and the real gas, but at higher pressures there is more and more difference. And when I look at 300 bars in this table, I can store 21 kilo in 1 cubic meter. So 0.6 cubic meter times 21 kilo per cubic meter is 12.6 kilo. When I would calculate this with the ideal gas formula, I would have 16.2 kilo. Then what is the real efficiency of fuel cells? There is a test of the Austrian Automobile Club. They tested Hyundai EX35, and they make the efficiency test by the Technical University of Vienna, and they stated a complete difference between 30 and 39% depending on temperature. That's a little bit lower than you have expected from all the advertising about fuel cells, but this is the reality. For the house, we can assume 39% because we will have always the ideal temperature. So 1 kilo hydrogen has 33.33 kilowatt hours chemical energy times 39% is 13 kilowatt hours electricity. And when we multiply this with the 12.6 kilo hydrogen in these 12 big bottles, then we have 163.8 kilowatt. Now let's assume we calculate it 2 times wrong. We calculate it with the ideal gas, and because we hear so much advertising, we assume the fuel cell with 60% efficiency. Then we have nearly double, 324 kilowatt hours instead of only 163 kilowatt hour. By the way, the gas bottle storage has more weight than lithium iron phosphate batteries to store 163.8 kilowatt hours. So hydrogen is very bulky and heavy, as long as you have not very expensive carbon fiber tanks and so on. So here you have a battle between efficient battery against cheap hydrogen. Battery vs hydrogen in the day-night balance, the efficient battery wins, because I can split the purchase price of the battery to several hundred usages per year. But when I have only one usage, I have to take the cheapest option, and even when the efficiency is very low, the cheapest option, hydrogen, beats in this case at summer-winter balancing the battery. But is there not a way to make it even cheaper? Yes, proposal 4, the external service provider. Let's assume when we have not enough own electricity, we purchase at this external service provider for 40 cents per kilowatt hour in Oslo and more south for 30 cents per kilowatt hour. And we sell him a lot of electricity when we have enough of it in the summertime for 4 cents in Oslo or only 3 cents in other areas. And he needs 4 kilowatt hours delivered to give us back 1 kilowatt hour, because there is always efficiency of the storage and to make again electricity, but it's still cheaper. Why is it cheaper? At this bottle storage, we have about more than 10 euro per cubic meter. But a big underground gas storage has costs of less than 1 euro per cubic meter at normal pressure, to be exactly. Next problem, 1 cubic meter hydrogen has only 3 kilowatt hours, while 1 cubic meter methane has 9.97 kilowatt hours. So there is a huge difference in the storage cost. The next problem is, I assumed about 3,000 euro per kilowatt for the fuel cell, and the fuel cell has only 39% efficiency. And on the other side are combined cycle power plants. They have only 1,000 euro per kilowatt cost, and they have 60% efficiency. This is the reason why the external service provider is in this case the cheapest solution, because he can use much different technique and much cheaper technique. Let's see a scale of efficiency in summer-winter balancing. Even in Oslo, only when the efficiency is below 25%, the house has not enough energy to make all the energy itself. And between 14% and 20%, this would be small equipment with internal combustion engines to use hydrogen. At 20 to 25%, we would have small equipment with fuel cells. And between 25 and 30%, we have power to methane, power to hydrogen, power to methanol, and combined cycle power plants. And above it, we have no solution what is cost efficient, but maybe in the future there will be something what is cheaper than a battery and more efficient than the power to methane and combined cycle power plant cycle. But before the seasonal balance becomes topical, we have to solve the day-night balance. This is in summer 2020, in June, the week with the longest days. We see here always the yellow, this is solar energy in Germany, but it's still not enough. There is more energy demand than this yellow solar energy is in the table. And in the night, we see nothing from solar energy because just right now it's not stored. It's only delivered to the grid as it appears. The sun shines, we deliver in the grid. The sun does not shine, nothing happens. So we have to expand solar energy very much. We have to store the solar electricity to deliver it also in the night. And seasonal balance becomes topical when there are in Germany 300 gigawatt of photovoltaics and 750 gigawatt hours of batteries. Before, we can think about it, but it's before other things, the day-night balancing, more important. This was another video from Roland Mösel, founder of Planetary Engineering Group Earth. And as always, like, comment, subscribe, hit the bell button to be notified when I make another video.